Question 6. When you look into a crystal ball, which is a sphere made of glass, what sort of lens does it behave like? Is it a concave lens, a convex lens, not a lens, or is there not enough information to tell? Well, in fact, there is enough information to tell, because we're told that we have a sphere. Now, a sphere bulges outwards everywhere, right? So as long as we're starting from outside the sphere and looking into it, like the question asks, then it must behave like a convex lens. It always bulges outwards, and that means it's convex. So B is the correct answer. Question 7. Which of these does not contain any lenses? Windows, spectacles, telescopes, or digital projectors? Let's go through them. Digital projectors use lenses in order to focus an image and prevent it from becoming blurred. If the lens of the projector doesn't have the exact focal point, then the image will become very blurry, because instead of being focused on the screen, it's focused at a point in front of the screen or behind the screen. This means that it doesn't look very clear. But if we have the lens in just the right way, if we have it set up in just the right way, then we can get the light to focus exactly on the screen, which gives us a very sharp image. How about telescopes? Well, these are a magnifying machine. They use convex lenses to magnify starlight so that it's easier to see with our eyes. This means that we can see very faint stars and planets that we can't see unassisted. Alright, how about B, spectacles? Well, while some spectacles use concave lenses, more spectacles use convex lenses. However, all spectacles must contain lenses, or they won't have any effect on how the person wearing them sees. You can imagine that glasses without lenses that are bent would look very similar to glasses without anything in the frames, as if we're just looking through without any change to the world around us. The only difference is, if we didn't have a lens for the spectacle, we could still get it smudged or dirty. So the lenses of a pair of spectacles or a pair of glasses are the reason that it changes the way you look at things. So our last option is A, windows. And windows are not in fact lenses because they are not curved. So a window pane is perfectly flat. This means that a beam of light passing through it, even though its direction will change while it's within that glass, it will change back once it exits and end up being exactly the same as what it started. So if we have a number of parallel rays of light, then they'll end up also being parallel when they exit the glass. What this means is that we don't change the shape of the wavefront at all, which means that we have no lens at all, simply a block of glass that's causing a little bit of refraction. Remember that although lenses work on the principle of refraction, not everything that causes refraction is a lens. Lenses use refraction to bend light in specific ways. Question 8. What happens when parallel rays of light fall onto a convex lens? So we have a convex lens bulging outwards, and we have light falling onto this lens. What will happen is that the parallel rays of light will focus onto a particular point. If we were to draw a diagram of a convex lens, it might look something like this, right? So the next question, instead of asking about parallel rays, we'll ask about light coming from the focus. What happens when light from a point shines onto a convex lens? In this case, we're basically running the same experiment in reverse. Instead of light starting off parallel and getting focused to a point, it'll start off at a point and get focused to parallel. So if we run the same thing in reverse, it appears exactly the same as if we run it forwards. This is because the change in the angle of incidence and the angle of refraction depends only on what the lens is made out of, and not which direction the light is going. Question 9. How does the wavelength of a beam of light change as it passes through a convex lens? Well, what affects the wavelength of light? It's affected by how fast the light is going. Now, when we pass into a lens, we slow down. If we slow down, how does our wavelength change? Well, V equals f lambda, f doesn't change, shows if V slows down, then lambda will also decrease. So as it enters the lens, the beam of light will slow down and its wavelength will decrease. When it exits the lens, it'll speed up again and it will resume its original wavelength. Alright, well B asks, how does the wavelength change in a concave lens? Now, concave lenses are of course shaped very differently to convex lenses. But once again, we're still going from air into glass and back into air. So the wavelength will change in the same way as it did for a convex lens. Its wavelength will decrease as it slows down when it enters the lens, and increase when it speeds up when it exits the lens. So in this case, we can see that lenses, even if they have a very different effect on the shape of the wavefronts of light, will have a similar effect on the velocity and wavelength of the light. Question 10. Draw a diagram to show how a magnifying glass can be used to focus light from the sun onto a single point. Now, what would this look like if we saw it in real life? How does the focusing of a beam of light sort of manifest in the real world, if at all? Well, if you've ever burned a leaf using a magnifying glass, you'll know the answer. It looks something like this. The sunlight comes down, passes through the lens, and gets focused onto a single point, which is the very bright spot at the bottom of the picture. It's even possible to start fires like this. However, this isn't really the diagram that we've been asked to draw. So what we need to do is turn this into something that's a little easier to look at and a little easier to understand. And that will look something like this. We have the lens in the middle of the picture, and the parallel rays of light from the sun coming in from the top of the picture. We can see that when the rays of light pass through the lens, they bend and get focused into a central point called the focus point. So this means that all of the energy coming into the lens, spread out over the whole lens, is being pulled into a single point. That means that the light at this point will be far more intense and have a far larger concentration of energy than when it first reaches this lens, which is why we can create very, very high temperatures by using a magnifying glass to focus light from the sun onto, for example, some tinder for starting a fire. Well, that's the end of the questions, which means we're at the end of the lesson. So we've learned about lenses, in particular convex and concave lenses, exactly how they change the shape of a wavefront, and what they're useful for in our everyday life.